Okay. Actually, as you are aware that this is a two-credit hour course, and the main topics that we are going to, or the major or broad topics we can say that we are going to study in this course are: the first thing is combined stresses in beam elements. By combined stresses, I mean that you have already studied the flexural stresses or the shear stresses or torsional stresses for that case. Now we will study the combined effect if all of these stresses are acting on any structural member. So it is just basically the application of the flexural stresses or shear stresses which are or even the normal stresses that are acting on the beam element. This is the first topic that we are going to study. The second thing that we are going to study are the stresses or state of stresses acting on any particular point in a beam element or any element. We will study that how much stresses or what are the different types of stresses that are acting on any point. And for example, if we have a beam element and this is one element or this is one small section on this beam element, we will study different type of stresses that are acting on this element. And on this element, for example, these are the normal stresses, these are the shear stresses which are acting on this element. Then we will study or we will transform. For example, this is an element that we have cut at 90 degree to the plane of the beam. If we have another element that is at some inclination to the beam axis and we want to calculate the stresses on this inclined axis, so for that purpose we have to study the transformation of these stresses. For example, we have the stresses or the stresses which are at 90 degree to the element, and if we want to transform it at some axis which is inclined to these 90 degree axis, then we have to study the methods to transform these straight stresses to the inclined stresses. And for that purpose we have analytical equations, or we can call it as mathematical equations as well. And also we will study the concept of Mohr circle. And Mohr circle is quite easy method or quite convenient to transform the straight axis to the inclined axis. The fourth thing that we are going to study is transformation of strains. Just similar, just consider this element again. And if we have some strain that are acting on this element, then we will study the transformation of these strain to the inclined plane. And the same procedure is used. There are analytical equations for the transformation of strains, and also there are Mohr circle for the transformation of strain as well. The fifth and the major topic of this course is unsymmetrical bending. Up till now, we have been studying the symmetrical bending, or if you remember, you have studied this flexural formula, sigma f is equal to my over I. This formula is applicable when the load that are acting on the beam are exactly vertical or at 90 degree to the principal axis or to the axis of to the central axis. Now, if the loads are acting at some orientation, then the stresses are not, the deflection is not only in one direction. The deflection will also in the x plane and also in the y plane. So, to study the combined effect of this deflection, or to study this type of bending is called as unsymmetrical bending, and to figure out the stresses in the case of unsymmetrical bending, we will study this particular topic, and we will calculate the stresses, we will calculate the inclinations of neutral axis and these kind of things in this topic. This is one of the major topic and covers and carries highest weightage in the exam, even in the quizzes as well. The other topics that we are going to study is cylinders, or the stresses in the cylinder. There are different type of cylinder, for example, thick and thin cylinders, and there are different stresses in these cylinders, like longitudinal stresses, hoop stresses, and we are going to study this one as well. Next thing is we will study columns. In MOS1, you have studied the columns on which the loads are acting directly at the center. For example, if this is a column, then the load is acting directly on the center of this column. These are the centric columns. Now, in this course, we will study the stresses which are developed in columns when eccentricity is being, or the load is acting at some eccentricity. For example, let's say load is acting at this point. Then we have some eccentricity with respect to centroidal axis. Previously, the load was acting directly at the centroidal axis. Now the load is acting at some distance from the centroidal axis. So to calculate the stresses when the load is acting at some distance from the centroidal axis, we will study some method how to figure out the stresses in this case, how to design a column in this case. So this is another topic, and the final topic that we are going to study are theories of failure. These are classical theories which are proposed by some scientists or some back in 1800s, and this is basically a theoretical topic in which we will study the criteria of failure for different elements, and these include the Mohr column theory, the Tresca yield theory, and these different scientists have proposed different criteria. For example, if this person says that the failure occurs when the stress increases the ultimate stress, then this person might have said that the stress would increase as that the material will fail when the stress increases the yield stress. And everyone has different reasons. So we have to select the best theory and apply in our numerical problem. And these theories are applicable for all elements. For example, for columns as well, for cylinders and for beam elements or for frame elements. So these are the major topics that we are going to study in this course. And the books that you need to follow is obviously the first one is Strength of Materials by Pytel and Singer. The second book that you need to follow is Mechanics of Material by Hibbeler. These are the two books that you need to follow, and these two books have all the topics that we will be discussing in the class. But again, I would suggest you to make your own notes. Note down all the lectures, solve the numerical problem, because I may be solving numerical problem from different books, and I may use different sign conventions or different or slightly different formulas during these numerical problems. So if you are not going to make your notes, you might find it difficult when you solve the numerical problems from these two books directly, particularly in the case of this sign convention. They are very confusing, and you have to be very attentive in the class to understand these sign conventions or the formulas that we are going to use, because every book has different sign convention and things can get very confusing. So I suggest you to make your own notes uh, to have a better chance of performing well. So any question about this course content or books, you can ask me. If not, then we can start with our first topic, that is combined stresses. If you remember in MOS1, you have studied this formula, which is called as flexural formula, which shows that sigma F is equal to, or flexural stress is equal to My over I. So can anyone tell me that whether this stress is the normal stress or acting parallel to the cross section of any element? Abdullah, is this a normal stress or parallel stress to the axis?
Sir, I think it is the combination of both.
How can it be a combination? For example, let's say this is a beam.
Yes, sir.
This is the centroidal axis. These are the supports of this beam. Okay. If I cut the section from this axis, this is the section. And if you remember, you would have plotted the distribution of flexural stresses.
Yes, sir.
This is the distribution, right? So these stresses are basically, now this is the cross section of element, and these stresses are basically acting normal to the cross section of this beam. And these are the flexural stresses. It can be, for example, in this case, I have plotted the compressive on top and tensile at bottom. But it again depends on the type of loading or the direction of movement. So you don't have to worry about it at this stage. And this is just to show you. So at top we have the compression stress, at bottom we have the tensile stress. And if I represent the force, then I can represent it on this element. For example, if this is the element, then the force is normal to this uh, element or to this cross section of the beam element. So in this formula, you know that M is the moment which is acting at that particular, for example, if I want to calculate the stresses at this cross section, then I will figure out what is the moment at this cross section, y is the distance from the centroidal axis to the point at which I want to calculate the stresses. For example, in the question, it may ask you that calculate the flexural stresses at a distance of 2 meter from the left support. Then this cross section is at this distance. Okay, so firstly I would calculate the moment at this cross section. Then it would also tell me that where is this fiber located with respect to the centroidal axis. That means that it will also give me this particular distance. That, for example, calculate the stress at this point. Now if this distance is, let's say, 5 meter, then the y distance I will substitute is 5 meter, and I, you all know, is the moment of inertia. So this is just a brief review of application of this flexural formula. So you will substitute all the values and you will get the flexural stresses. So one thing is that these flexural stresses are normal to the cross section. And similarly, if let's suppose if on the same beam we have this normal stress, that is the normal load that is acting on this beam. Okay, due to this normal load, also the axial stresses are produced that we define as load over area. Now, if I want to represent the variation of this axial stresses, I will show on the same beam element. Let's say this is the beam element, and the variation would be something like this one. Okay. Now, what does this shows? This shows that let's just compare both these stresses. This is the axial stress, and this one is the flexural stress. Okay. So now, when the normal load is acting, or when this load Q is acting on the beam element, the normal stress or the axial stresses are produced. These axial stresses are uniform throughout the whole depth of the cross section. But in the case of flexural stress, we know from the formula that flexural stress varies with this y distance from the centroidal axis. As the y distance increases, the flexural stress increases. Flexural stress increase with y distance. Okay, but in the case of axial stresses, if you look at this formula, axial stresses does not depend on any y distance or on any distance from the cross section. It only depends on the force and the area of the cross section. For example, if I take the cross section at this particular point, the area would remain same. If I take the cross section at this point, the area would again be same, because the cross section of whole beam is same, right? So area remains same, this force remains same. So that is why these axial stresses remains uniform with respect to distance from the centroidal axis. For example, if in the question, if it asks you to calculate the axial stress at this B point, then for example, if this axial stress is 10, then at B point, the axial stress is again 10. Similarly, at this particular point, it will remain 10. But in the case of flexural stresses, the values change with respect to distance from the centroidal axis. So so we have two types of normal stress. Again, if I want to show it on the cross section, I will show it something like this one. So this is also the normal stress. So we have one normal stress as flexural and the other normal stress as axial. So if in a question it asks you to give me if there are two loads, this P load and this Q load acting on the element, and it asks you to give the stress at this point A, then the stress at point A would be sigma naught plus minus sigma f. And what is sigma naught? Sigma naught is Q over A plus minus what is sigma f my over I. So this is the whole idea of combined stresses. Previously, we were calculating the stresses, or we were calculating these simple stresses, or for example, in the question it would ask you to calculate the flexural stresses. You will simply apply this formula my over I and you will get the flexural stress, or it may ask you to calculate the normal stress or axial stress due to this force Q, and you will apply this formula. But now if it asks you to calculate the total stress at any particular point, you have to study, or you have to report the combined effect of axial stress and the flexural stress. But again, it depends whether this load Q is acting or not. For example, if only this load P is acting on a cross section, then you don't need to uh, calculate the axial stress, because axial stress is obviously due to the normal load acting in this particular direction. If I call it as x direction, then it is due to the load acting in the x direction. But again, if the load is acting inclined to this beam element, then we will have two resultants, one this P and other one parallel to the x direction. So we will have the axial stress as well as flexural stress. And this positive and negative sign depends on whether these stresses are in tension or compression. For example, if I am calculating the stress at this B point, then from flexural formula I can see that the stress is compressive at this B point. And from the axial stress diagram, I can see that the stress is tensile. So for this B point, if I write the equation, my equation will be, this is tensile, so I can take tensile as positive. So the equation will be Q over A minus My over I. So this is the combined stress at 4 point, let's call it as D. And similarly, if I want to calculate the stresses at this E point, then my equation will be slightly different, and it will be, now you can see that this stress or flexural stress is also tensile and the axial stress is also tensile. So in this case, both of these will add up. So you have to take care of this sign. It can be positive or it can be negative. Even the sign of this axial stress can also change. For example, in this question, I have shown it as tensile. So it is quite possible that it is also compressive. For example, the distribution is something like this. In that case, it will be negative in both cases because it does not vary with the distance. So you have to be slightly careful about the sign convention. And there is another type of stress, that is shear stress, for which the formula is this one. So can you tell me what is Q in this formula? Anyone?
Sir, applied load.
What is V?
Shear.
V is the shear force.
Yes,
Actually,
sir.
this Q is slightly different than the applied load. You may have to revise your notes. So let me just briefly tell you. For example, if this is the cross section, let's suppose I have this beam and I want to apply or I want to calculate the shear stresses. Previously, we were studying the normal stresses which are normal to the cross section, but these shear stresses are not normal. For example, if this is the element or this is the cross section, then these stresses are acting parallel to this side, to this side. These are the normal stresses and these are the shear stresses. So in this formula, we cannot add the normal stress, the shear stresses. This is only for the normal stresses. But again, at any particular point, these normal stresses also occur, the shear stresses also occur. So we have to calculate all these stresses. Okay. So coming back to this beam, if we have this beam and on which some load is acting, and I want to calculate the shear stress at this particular point, and in the cross section, this point is located somewhere over here, right? So what will be my first step? First step is I will figure out the shear force at this point. And from bending moment diagram and shear force diagram, from shear force diagram, you know how to calculate the shear force at any point in the beam. You will calculate these reactions and then you will plot the shear force diagram, or you can directly figure out what is the shear stress at this point. For example, in this case, it is 5. So the value of V will be 5 kilonewton, let's call it. And then I have to figure out Q. Now Q is very important thing. Q is basically the moment of area above the centroid. Okay. By the way, if I show that this, okay. Q is basically the movement of area above the centroid. For example, in this question, if it asks us that you need to find out the shear stress at this particular point, let's call this point as B, then the area above this point is this area which I have shown by shaded portion. I have to calculate the movement of this area about the centroidal axis. So what is the moment of area? Firstly, I would calculate, for example, if this is the area, then I would, if let's call this small rectangle as 1 and this one as 2, then Q is equal to area multiplied by distance of the centroid of this area to the centroid of the whole body. So if I want to calculate the stresses at B, I have to calculate QB. What will be QB? It will be the area or moment of this total area. So I will divide this area into two parts, this 1 and this 2. And if this distance is 4, this distance is 2. What will be the area of this one section? That will be 4 into 2, right? And what if let's say this total distance is 5, what will be this distance from the centroid of this area? That will be 1. And what will be the distance, or what will be this y dash distance? Y dash distance is the distance from the centroid of this area to the centroid of whole shape. So for centroid of whole shape, the distance is 5. So I want to know this particular distance from the centroid of this shape to the to this point. And what will be this distance? That will be 4. So QB will be, I have calculated Q for this particular area, but I have this small area as well. So let's suppose this distance is, let's call it as 2. I'm just assuming the values. These are not the final values. This distance, if it is 1, and this distance, let's call it as 3. So for this 2 area, I have 3 multiplied by 1, and y distance is again 2. And then This is how I will calculate this QB. So QB, what we are actually doing, we are calculating the moment of area. First, we are calculating the area, then we are taking its moment about the centroidal axis. So this is how you are going to figure out this Q factor, and this I is the moment of inertia of this I section, or if it is a rectangular section, then you will calculate the moment of inertia, and this B is the width at the point on which we want to calculate the shear stresses. For example, we are calculating the shear stresses at this capital B point, and at this point the width is 1, so this value will be 1. And you will substitute all the values in this formula, that is tau is equal to VQ over IB, and you will get the value of shear stress at any particular point. And the distribution of shear stress is something like this one. It is 0 at top and bottom and maximum at the centroid. So it is quite different from what we did in the flexural formula. In the flexural formula, it is maximum, flexural stresses are maximum at top and bottom and 0 at the center. But if you calculate the shear stresses at different points along the cross section, you will see that it will be 0 at top and bottom and maximum at the center. Can anyone tell me that why it is maximum at center by looking at this formula? Abdullah. Waqar bhi aa gaya.
Yes, yes, sir, वकार भी आ गया.
Waqar. Why shear stress is maximum at center with respect to this formula? बुखार चला तो नहीं गया?
No, sir.
मैं ख्याल वो सो गया दोबारा से.
नहीं, sir.
नहीं पता सर.
Just look at this formula and try to figure out why it is maximum at center. What factor will change with respect to cross section? If I write the formula like this one, tau is equal to V cross A cross Y divided by I into B. Okay, so this shear force will remain same if whether I am calculating the stress at this point or at this point. This I will remain same. This B will change obviously, but the major change is this area. For example, if I am calculating the shear stress at this point, then I have to take the area above this point, and that area will only be this small rectangle. Okay, but if I am calculating the shear stress at this particular point or at the centroid, then this area will be this small this horizontal rectangle and also this rectangle as well. So the area will definitely increase. So when I am at the center, I will have maximum area above this point, and therefore this area will be maximum, and that is why the shear stress will also be maximum. And another important point that you have to keep in mind, that this moment of area, I am taking the area above the point at which I want to calculate the shear stresses. But let's suppose if I am calculating the shear stress at some point that is below the centroidal axis, then you have to consider the area below this point. Okay, so just keep this thing in mind. It will just flip. Okay, so if you are calculating the stresses at some point above this cross section, then you have to consider the area above this point. But if you are calculating the stress at some point below this cross section or below the centroidal axis, then you have to consider the area that is located below this cross section. Actually, I am not going into the derivation of this shear stress formula because that is not in the scope of this course. So I'm just letting you know how to apply this particular formula, and finally you will get the stresses. These things will get clear once we solve one example problem. Okay, so Any question about these combined stresses?
एक्सक्यूज मी सर।
Yes.
सर आपने जो आई शेप के लिए डायग्राम बनाई है वो किसी और टाइप की बीम के लिए भी सेम रहेगी?
This diagram.
यस सर।
Yes. Even for the rectangular shape, it would remain same. For example, if you are at this point, the area above this one is 0, so the stress will be 0. If you are at the center, you have the maximum stresses, and if you are at the bottom, you will have the again 0, and the diagram will remain same.
ओके सर।
Let's solve one simple problem. Let's suppose I have this beam on which the load of 4 kilonewton per meter is acting. The length is 6 meter. This is the cross section. Okay. And the height is 180 millimeter. No, actually this width is 120 millimeter and the height is, okay, yeah, it is 180 millimeter. And I want to calculate, in this question, we have to calculate the shear stress at a distance of 1 meter from this support and at this particular point that is located at 60 millimeter from the centroidal axis. We have to calculate the shear stress only. I'm not saying the combined stresses or the flexural stresses, just the shear stress at this particular point. And first thing, you have to write down the formula and see what factors you need. You need the shear force at this point, that is at 1 meter, because it has been asked in the question that you need to figure out the shear stress at this particular point. And in the cross section, if I see this point is located over here, we need to figure out Q, I, and B. So can you tell me what will be the shear force at this section? What will be this fraction?
Say 12.
6 into 4, 24, and half of that will be 12. Okay. What will be the shear force at this point?
12.
12. What will be the shear force diagram? If this is 12, this is 12. What will be the shear force over here? This 12, and it will go on something like this one, right?
Yes, sir.
So what will be the shear force at 1 meter distance? Can I say that shear force is 12 minus 4 into 1? 8 kilonewton. Is it
Yes,
so?
sir.
Yes, sir.
So the shear force at this point is 8. V is equal to 8 kilonewton, right? And next thing is I have to calculate this Q factor, that is the moment of area. So this is the point at which I want to calculate the shear stress. I have to consider the area above this point, which is this shaded area. Okay, so Q is equal to A into Y distance. So what will be the area? What is this area?
60 into 120.
How much?
60 into 120.
Above this point, this shaded area.
Oh, yeah, yeah.
What is this distance?
30 into 120.
This distance will be 30
30. Yes, sir.
and the width is 120. And what will be y distance? Or what will be the value of y? Y is the distance
75.
from here till here. So that will be 75. So
Yes,
what
sir.
is q?
Sir, 270,000.
270,000. Okay. So this is in millimeter cube. Just
Yes, sir.
remember the units. What will be the value in meter cube? Yeah, I have to divide it by 1,000 three times, right?
Sir, 2.7 into 10 power minus 4.
2.7 into 10 raised to power minus
4.
4 meter cube. Okay, so now I have V, I have the Q value. What will be I for this cross section? This is a rectangular cross section, so we have simply BH cube over 12. So width is 120, height is 180 divided by 12. So what is this value? Give me the answer in meters.
Sir, 5.832 into 10 power minus 5.
5.83 into 10 minus 5 meters. So now I have I as well, and the final thing is this B. What is B at this section? So B remains same for the whole body, but at this point the width is 120, so I will use that value directly. So the shear stress will be 8 into uh, Q is 2.7 into 10 raised to power minus 4 over I is equal to 5.83 cross 10 minus 5, and width is 120 or 0.120. So what is the shear stress at this particular point?
Sir, 308.75.
30, or let's call it as 309 kilonewton per meter square. So this is the shear stress at this particular point. So this is how you calculate the stresses at any particular point. So in this question, I just asked to calculate the shear stresses. Uh, so in the next class, we will solve one problem of the combined stresses where we have to calculate the shear stresses. For example, even in this one, you see that there is some value of bending moment at this particular point. So there are normal stresses as well. So if you want to report the total state of stress at this particular point, you have to report both the shear stresses and the normal stresses. So for now, I leave it up to you to calculate the flexural stress at the same point uh, along the length and at this particular point in the cross section. So for that, what will you do? You will calculate the moment at this particular point. You will calculate the y distance that is given, that is 60 millimeter, and I you already know, and that will be the normal stress at this particular point, and that is the total stress in the case of this particular question. So For now or for this class, this is it. And in the next class, we will study one problem or solve one problem related to the combined stresses. So if you have any question, you can ask me.
No, sir.